Right, let's get started. As you see from this schedule, today we will have another special guest lecture by Professor Jin Park. He has been a long experience with Hyundai Heavy Industry as a CTO. He will guide us on her strengths topic today. And on Thursday, we will return back to our regular class. And then Friday, we'll have a trip to Creosote between 12:30 to 15:30. I have a list of participants as like this one. We have 14 students and 3 of us of TA, and there are 5 cars available. So we will have a trip, nice trip to Creosote on Friday. Will let you, or TA will let you know that each group of car members by Thursday. So you can join with the driver together. Any question on schedule or other items? No, then we can invite Professor Park for his lecture. Park, can you share your screen with the audio checkbox and then okay, start the lecture. I can see, yeah, the slide is coming. You can start your lecture.
한 교수님 화면 공유되고 있나요?
Yes, yes.
소리도 괜찮고요.
Yes, sound is good.
Yes, thank you. Let me start. Thank you, Professor Han. Hello, everybody. Good afternoon. Very nice to meet you in class ME43, Introduction to Naval Architecture and Ocean Engineering. And my name is Jin-Soo Park. I've been working for Hyundai Heavy Industry in the shipbuilding company. Currently, I'm working on research cooperation between KAIST and Hyundai Heavy Industry Group. My major is structural design and analysis, and ship is one of the products that I have worked on. Today's topic is hull strength, strength of ship structures. In this presentation, I'm going to focus on the concept. I'll try to avoid the details. I think most of you are unfamiliar with ships and shipbuilding industry, so I'll try my best to introduce the subject simply and conceptually. In general, when we are talking about ship design, there are three main things that we are most concerned about. First, it's performance, like how fast ship runs, or how large amount of cargo it can carry. Speed and cargo volume are very important aspects. Second, it's safety. It should be strong enough during the lifetime. I mean, it should be strong in order to endure the severest loading. the ship may possibly encounter during her voyage. Third, efficiency or economics. We should have good value to construct and maintain from a point of cost against the benefit. It should demonstrate low fuel consumption as well as low maintenance cost. Generally, these three elements are considered together in the initial design stage and optimized to get the best design solution. Today's topic, hull strength, is related with a second concept, safety of departure. Before we get into the subject, hull strength, I'd like to show you an interesting example of strength test of small structure, soda can. It is probably very familiar with you. However, you may have never thought about its strength. How much weight can this soda can hold? It's an interesting question. Soda can generally is very thin, less than 0.3 millimeters aluminum, to make it very light. But also it's supposed to be strong enough to act a kind of liquid container. In this slide, you see two test situations. The left one is opened and empty can. The can is vertically loaded and it collapsed 55 kilograms. The photo shows just a little bit after the load reached the maximum. On the other hand, in the right one, the question is how much load can this soda can hold in the unopened and liquid full condition. Actually, this unopened can undergoes many types of heavy loadings, like a large stack of soda can boxes on top of each other, as you know. Now let's see the test of unopened can.
In aluminum tank, like soda can or space rocket, it's going to be much stronger when there is some pressure inside.
Like much stronger.
So I'm going to say that it's going to be at least twice as strong with the soda in it. So here we go.
How much stronger can you guess? Twice, times, over 100, over 200.
Whoa. Oh.
300.
Oh, it's going to go.
Oh, can you see the ripples, deformation ripples on the shell in the pot? Finally, it ruptures.
That was really nice. Yeah. And let's see the result. 360 kilograms, so way more. Yeah, that was really nice. And it failed like really slowly first before exploding.
Yeah, how much load did you see? it went up to 360 kilograms, about 7 times stronger than the left empty one. I think this test shows very well the concept of structural strength. You can maybe imagine how the thickness of the can has been determined based on the consideration of many kinds of ultimate loading conditions. Likewise, ship hull strength should be designed to resist maximum loadings by proper design of structures. As you may know, the main target in this class is large commercial ships. In case of commercial ships, our main concern is how big load, what kind of loading can break the overall ship hull structure in 2 parts. In other words, what type of wave and cargo loadings should be considered for the hull structure to be strong enough and guarantee safety. Design purpose of hull strength is to ensure safety in ship's lifetime, 20 years. Here are some typical examples of photos showing the entire loss of hull strength, probably as a result of undergoing excessive wave loading. There must have been a big vertical buoyancy force at the center part. There seems to be fatal breakage by bending in the middle of the hull. These catastrophic structural damages very rarely happen during operation at sea, but it can also happen even though the probability is very low. The ship, especially when the ship encounters more serious wave loading than the design wave of lifetime. Generally, the types of ships are classified according to the kind of cargo the ship carries. If it carries grain, ore, and coal, it's called a bulk carrier. If it carries oil, it's called tanker. Likewise, container ship carries containers, gas carriers, LNG, or LPG. Car carrier for automobiles, cruise and ferry that carries people and cars. Warship is for battle. The overall shape and characteristics are similar, but the internal structures may be quite different from each other, depending on the cargoes and its functions. Among these ships, LNG carrier is the most expensive nowadays and most difficult to construct. One thing is most of LNG carriers now being operated over the world was constructed in this country, Korea. When when we talk about ship, it may be defined in many ways. In particular, when we limit our concern to general commercial ship can be defined as a large watercraft that travels the oceans and sufficiently deep waterways. Also, it carries goods or passengers with specialized missions. By the way, hull refers to the main structural part along the whole ship length, usually made of steel, sometimes made of aluminum. Main loadings against the hull are waves and cargoes. So hull should be designed to be optimized for low cost and sufficient strength in order to have the proper performance and require the strength. As main part of hull, there are cargo hold and bulbous power engine room, decals, and so forth. By the way, how big is general large cargo ship? Here is a good example showing how big it is. The largest container ship operating in the oceans currently, 400 meters long, about 60 meters wide. Cargo capacity, in other words, it's capable of carrying about 24,000 container boxes, which are 20-foot containers. It's so big. And more than 50% of the containers loaded above the upper deck, as you can see from this photo. It would be interesting to compare the length of this largest container ship with big famous structures we can see worldwide. In terms of length, it's bigger than Eiffel Tower in Paris, a little bit smaller than the Oriental Pearl Tower in Shanghai. If compared with the soccer field, about 4 times big as soccer field. I'd like to talk more about hull. Hull may be said to be a watertight body of ship. That is main structure part, including cargo holds along the whole ship length. Hull is supposed to hold many kinds of cargoes, also withstand external and internal loadings. Top part of the hull, so-called upper deck, may be partially open in order to manage cargoes. A structural complex, hull is composed of plate, stiffeners, frames, bulkheads, and so on. This figure shows the inside of 4 parts of the hull of bulk carrier, which carries grains or coal. It looks quite complicated and composed of many different types of structural elements. However, you see from this photo, the outside of the hull is quite simple and smooth. This slide shows typical mid part of hull structure in tankers. It's also composed of many kinds of structural elements, platings, primary members, web frame, and girder, and the secondary member of longitudinal and stiffness. Most of them are welded to each other. In general, the sectional shape and the arrangement of elements are similar along the whole length. In other words, they are repeated and at regular distance of several meters in order to be effective in manufacturing. To make a whole ship, a quite number of these blocks are transported into a certain place, as you see in the photo, and assembled together in the place of so-called a dock. For your reference, here is summary shipbuilding process. It is roughly saying contract, design, construction, sea trial, delivery. The whole process usually takes place 1.5 years. Among them, the construction process for the ship hull can be described as steel cutting, block fabrication, block assembly at the dock and ground, and then commissioning and outfitting at the keyword on the water. This photo shows a ship, very big shipbuilding yard where you can see, you can notice the work area and the antenna ship are being assembled together in a large dock. Other dock, you can see 3 ships are being built together. This photo shows a part of a big shipbuilding yard. You can see three big docks, and in each dock, usually 3 or 4 large ships are built together. At this point, I'd like to talk about basic concept of structural strength and safety. Here is a photo. 2 persons are crossing a bridge. At first glance, I think the bridge looks quite dangerous, doesn't it? You may wonder if it is safe or not. Is the bridge strong enough or weak? In order to answer the question, in other words, in order to think about safety and strength of the bridge, we first need to, have to consider all of the loadings that can happen in the bridge's lifetime. Whether it's safe or not primarily depends on the loadings, such as weight of the persons crossing the bridge, number of people, or their walking speed, frequency of crossing, wind force and direction, current state of the bridge condition. After all, the problem of strength and weakness is the problem of the relation between structure and loadings. If loadings are too severe and heavy, structures become not strong. It becomes weak. So designing structures eventually means determining the size and thickness and arrangement of structural elements based on the design loadings for its lifetime. In this slide, I'd like to briefly explain the design concept of hull structure. Basically, hull is designed. Hull is designed to be structurally safe and functional in the lifetime of 20 years under maximum wave loading and repeated small and medium-sized wave loading, various kinds of cargo loadings, many accidental loadings such as slamming, impact, collision, etc. I'm going to talk about those loadings in more details later. From a point of failure, hull structure should be designed for properly for cracks and buckling and fracture that do not occur during the lifetime. Usually, the largest wave loading condition happens under the sagging wave, like figure, mid part of ship may bend down and both ends go up. Also, cyclic loading may continuously happen by encountering repeated wave loading. When designing ship hull, the main external loading is wave loading. In reality, there are so many kinds of waves that we meet when we sail at sea. From design point of view, we assume that a ship encounters about 100 million waves in 20 years. Some waves are regular, the shape of height and length uniform like this. Some waves are irregular. The wave profile is not uniform, changes all the time, like this figure. In terms of wavelengths, there are so many different lengths of waves compared to ship. As you can see, some examples in this figure. Among them, this red color shaded situation where the wavelengths is about the same as ship lengths, then maximum, I mean the worst wave bending moment occurs. Besides, continuous cyclic loading is also applied by repeated irregular waves. I'd like to add some more about the bending moment, especially a case the bending moment becomes maximum. The total bending moment can be divided into static and dynamic components. Static is due to cargo load distribution along the ship length. Dynamic is due to wave loads. The maximum static moment happens when the center area cargo hold is full and the other end part cargo is empty, like this figure. And then maximum static moment occurs. Maximum dynamic moment happens when the ship encounters a wave whose length is about the same as ship length. Just I mentioned before. When the ship is laid on the wave like this bottom, the figure, the top position of wave is located at both ends of the ship. This is the case of sagging, which is our most concern when designing ship. And the worst condition occurs, unfortunately, these two maximum static and maximum dynamic situations happen at the same time. This is one of the cases that structural designers are most concerned about. Here are many photos showing possible situations that ship experience in rough seas. Basically, ship hulls are supposed to be designed to withstand the wave loadings in such storm seas. Sometimes we can expect ultimate loadings due to bow flare impact or bottom slamming or quite big wave height. Of course, most of the time during the voyage, sea states are not so severe. However, we believe we cannot evade the ultimate loading, but eventually we have to meet such severe loadings. So we need to design hull against those severest loadings. So hull designers always think which is the most critical condition. Next topic is weak areas in ship structures. As you know, in human, our body, which part do you think is the weakest? It varies a lot from person to person, but we may think that waste in our back is the part we feel many troubles, especially as we get old. In the same manner, in the ship, the mid part, upper deck and bottom plate amidships are the weakest areas in general. At midship, a maximum bending moment is applied, inducing maximum stress, sometimes resulting in structural failure, such as cracks or the buckling. Cracks maybe initiate, grow in time slowly. Sometimes large stresses maybe induce split and beam buckle. I mean, a large deformation and the buckled shape becomes larger, so-called post-buckling, and reaches a final collapse. So hull design criteria should be such that cracks, buckling that do not occur during the lifetime of ship. For this purpose, hull designers determine thickness and arrangement of structural elements, considering many kinds of serious loading. This figure shows a hogging deformation of ship under big hogging wave, mid-hull bent upward and both ends bent down. In these structures, most common structural failure is cracks. Cracks may be defined as very narrow gap between two things. In this case, a separation of material in steel plate or beams frequently at welded joints. Cracks may occur at the weakest points and propagate across the deck bottom in many places at stress concentration areas such as bracket hole, welded connections, and so forth. This photo shows an example of crack growth at the deck. It grew as long as 20 meters, almost across the upper deck. Another type of most concern ship structural failure is buckling. Buckling may be defined as structural instability as large lateral deformation occurring under compressive loading at plate panels and stiffeners. A typical example of plate lateral buckling mode at compression is shown in this figure. In general, buckling, once the buckling happens, and post-buckling, that is much bigger subsequent to a lateral deformation follows, sometimes causing the final whole ship collapse. For example, under the hogging moment, in other words, the highest point of wave is at the center part of ship, then ship structure deforms center up and both ends down like this figure. This mode naturally induce the bottom structure experiencing compression. It may possibly cause buckling at the plate and stiffener at this bottom area. As you can see, a simulation of buckling mode, the stiffeners bent this way and that way. Plate forms up and down, red and blue. It is very interesting to see a bunch of adjacent plates undergoing buckling mode together in series. Sometimes we carry out full-scale buckling tests in order to confirm the simulation results. This slide, I'd like to talk about section of ship and the shape of section along the ship. Design of section is very important because it determines rigidity. Rigidity of structural section depends on the shape of section. It's closely related to the hull deflection. Here are some very simple examples of beam section A, B, C, and D. The areas of the section are assumed to be the same. Then the shape of beam A is stronger comparatively against the vertical bending. It's weak to lateral bending, maybe weak to torsion. By the way, beam B is weak to vertical bending. However, beam D, very effective for vertical, lateral, torsional movements. It's called a closed section. So the basic concept when designing hull sections is to make it a closed section as much as possible. If we need an opening on the deck in order to manage the cargo, then we should make the opening as small as possible. Here are various sections of ship. Oil tanker, two big closed sections in a whole one section. Car carriers has many decks inside so that it carries many cars as possible. Car carrier has both The weak vertical and lateral rigidity. Next, the bulk area, center cargo hold, and 2 side ballast tank, 3 closed sections in a big, 1 closed section. Container ship has to be big opening on the deck inevitably. So in this area, the thickness of the plate for the small closed section, these blue parts, should be increased enough. Thickness should be increased enough to maintain the rigidity of the overall section. LNG carrier is similar with having a big opening on the deck. In this slide, I'm going to talk about basic knowledge of strength materials. Some of you may not be familiar with this in general. We use concept for stress and strain. I think I'd better skip this section briefly. I just show you a simulation of stress relation specimen. We are running out of time, so I'd like to go for it. Stress and strain is very important technical terminology. Stress is regarded as a measure of internal resistance of material against external forces. There are 2 kinds of stress: normal and shear stress. Likewise, strain is measure of deformation produced by the influence of stress. So there are also 2 components, normal and shear strengths. Basically, all of the complicated structural deformation can be decomposed and expressed by these 2 types of normal and shear strains. And by Hooke's law of stress and strain relation, the magnitude of stress is linearized with the material property constant, Young's modulus, capital E. This E becomes bigger, it means it's harder to deform. Bigger force is needed to make the same elongation. In case of steel and aluminum, generally Young's modulus of steel is about 3 times bigger than aluminum. So we use steel for the structure undergoing large loading, because steel deforms 3 times less than aluminum, resists 3 times more force than aluminum. When we have an injection, why does it hurt? Because the section of needle is very small and stress on the skin are very, very large. So we feel kind of. This point, I think we need to talk about beam theory, simple beam theory, because hull structure of ship can be regarded as a simple beam. In this theory, maximum bending stress is in the middle is calculated by this equation. I'd like I better skip this section because we are running out of time. Okay. Simple calculation versus structural analysis. In the initial design stage, we usually use a simple beam calculation to determine the maximum bending stresses at mid parts using this equation. And the geometrical stress concentration factors. In this case, the bending moment is determined M empirically based on probabilistic approach and some formula of classification rules. However, in later detailed design, we carry out very complicated finite element analysis for evaluation of stresses at every part of her structure. In this detailed analysis, we apply actual variable pressure loadings over the ship outer surface, considering ship speed and variable wave height, wave angle and frequency, and cargo loading inside. This figure shows just one case of analysis loading under wave angle 180 degrees, wave height 14.5 meters, wave period is 11 seconds. And actually, we need to carry out a large number of structural analysis for all loading conditions. In actual design, the stress should be lower than about 90% of yield stress to prevent structural failures such as crack, fracture. For this purpose, a very tedious and complicated finite element analysis are often carried out in the initial and later design stage. Sometimes stresses should be much less than yield stress in order to prevent buckling, large deformation. Here are some examples of structural failures that ship can experience in operation at sea. Cracks occurs at upper deck, growing to final fracture. Cracks, bows, and side shell cracks and buckling is side part. From now on, I'm going to discuss loading situations against the ship. First of all, weight and buoyancy. As you all know, ship float. Weight and buoyancy. Ships float on the water because weight is equal to buoyancy. And it reaches vertical equivalence. Therefore, if weight or buoyancy change, ship comes to move to make another equivalence. In actual voyage, wave height actually usually continuously changes. In other, dynamic wave loading keeps applying to the hull structure, so ship inevitably and continuously keep moving. Here, I summarize main design loadings as Hurghada loadings: vertical and horizontal bending moment, torsional moment, Hurghada shocks. As impact loading, there are powerful impact, bottom slamming and collision, grounding, explosion impacts. Sometimes there are various kinds of cargo loadings. Sometimes vibration and temperature maybe act another kind of loadings. Now, here is a good video showing wave loading and ship response. but this
A simple understanding of the strength and forces acting on a ship's structure is also important. An optimal ship structure has the minimum amount of steel to provide the strength and stiffness necessary to withstand the full range of internal and external forces exerted on it, from sources such as the light ship weight, the weight of cargo, ballast, fuel, etc. And of course the harsh sea, marine environment, the movement of the ship and vibrations. The hull may be compared to a simple beam. When a force acts on the beam, it bends and stretches in accordance with the magnitude of the force and the strength of the beam. Loads generate vertical static forces in still water. Waves generate dynamic forces that act vertically, horizontally and transversely, also creating shear and bending forces, in addition to tension and compression. Longitudinal forces will be experienced in the bow due to ahead seas. So at sea, the ship's hull is continuously being exposed to a large number of forces coming from practically all directions. The same simple beam principle also occurs in complex combinations inside the ship's structure, where plating, frames, stiffening, girders, panels and brackets are built up from many separate small beam elements, all working together. Due to the many and variable forces acting upon them, these elements may partly fail and develop cracks and damage in critical areas, causing a serious reduction in local and overall strength. In addition, aggressive corrosion that is found when placing steel in the marine environment ruthlessly weakens the steel and its welded connection.
is very useful for our understanding. First of all, a vertical hull bending moment is the most important and the most critical loading when designing ship hulls. First, we can think about static component, which is still water bending moment due to cargo distribution. For example, when the center part is fully loaded and the other cargo is empty, then so-called sagging is induced, or deformation both ends up and center bottom. In the similar manner, when the center hold is empty, then the other holds are full, so-called hogging moment is applied. Besides, there is also dynamic, cyclic bending moment in wave conditions. So depending on the condition, tension and compression can happen cyclically and repeatedly at the deck structure as well as at bottom. Next loading is horizontal hull gutter bending moment. First, I'd like you to see a video for a ship motion simulation under a side direction wave. A big regular wave is coming from the right side of the ship, and ship begins to move into rolling motion. Under this situation, generally horizontal, sometimes lateral bending moment is induced with large rolling motion. Moreover, this horizontal bending moment is coupled with vertical moment, so the stresses at the upper deck corner may become seriously large. Sometimes, rarely though, it causes the ship to suffer from loss of stability and final rising. This photo shows a large container ship suffering from big side rolling with side waves. Another important hull buckle loading is torsional moment. Torsional moment and its subsequent torsional deformation usually happen in oblique wave condition. In other words, in case that a ship encounters a wave with 45 degrees against the force of ship. In this situation, water depths on the right side and left side cyclically change. And this difference of water depths at both sides induces torsional moment continuously and cyclically. In general, torsional movement is very critical to container ship, which have large openings at deck. We know large opening is comparatively weak for twisting deformation. Another type of loading against the shipper is impact loading. When ship sails under head sea, that is wave coming from the front with a wave direction of about 0 to 45 degrees. Impact loading may be happen on the bar flare, depending on the wave height and ship speed. In this slide, bar flare is meant to be the structure above the water in this area. Impact loading may cause permanent yield deformation. You can see in this photo an example of actual yield deformation. So the researcher designed bar flare impact pressure model tests are sometimes carried out using pressure sensors installed at bar flares. In many cases, we perform ship motion simulation considering both ship hull and water ground. You may notice high pressure, red color area on the bar flare under the head sea condition. Another type of impact loading is bottom slamming. This loading case often occurs for high-speed ship when ship is sailing in head seas and moving vertically in pitching motion. As you see in this simulation, when falling downward from vertical motion, very high impact pressure occurs over the front bottom area. Sometimes it causes permanent yielding and fracture, even though bar flare impact, bottom slamming, local loading. They also very often induces whipping, resulting in extra vertical bending moment. So it maybe makes loading conditions more serious in many cases. One of the loading conditions we need to consider when designing hull structure is collision, especially for oil tankers and gas carriers, such as LNG carrier. We often hear about an accident of ship-to-ship collision, as you see in this photo, where a large bulk carrier collided into small oil tanker. You can notice a big spillage of oil over the large area around the ships. So designers need to evaluate the strength of side structure against possible collision force to see if the side structure is penetrated or not when it's collided by another ship. In general, as you may imagine, it's very hard to test using full-scale actual ship. Therefore, numerical simulations are often carried out instead to evaluate side structures, considering collision speed and shape of the front of colliding ship. These figures show finite element analysis models or large oil tankers, LNG carrier. In this analysis, very large displacement and non-linearity evaluation and plate rupture are included to analyze penetration, usually very difficult to carry out. Another type of accidental impact is grounding. Grounding impact rarely happen accidentally when a ship runs aground or make contact with the ocean beds, rocks. Main point is to properly design the double bottom structures for liquid cargo, not spill out of the cargo when the grounding happens. For this purpose, numerical simulation for the double bottom against the grounding is often carried out. In this simulation, nonlinear tearing analysis for bottom plate is carried out. Another type is special loading is explosion. This case is kind of limited to warship. You may imagine many scenarios of explosion near or inside field. What warship structural designers should understand: the ship structure responds to underwater explosion impact, because they need to carry out proper reinforcement to minimize casualties and system damages. For this purpose, real explosion tests may be conducted, but most of the cases are evaluated using the technology FSI, fluid structure interaction simulation. In this simulation, ship structure and a large volume of seawater around the ship and explosive are included in the simulation modeling. Generally, it takes a lot of time and needs very skillful experience. Here is a good actual test conducted by US Navy. Warship structure response to underwater detonation of torpedo.
Contrary to popular belief, modern torpedoes do not actually have direct impact with the hull of the ship. Instead, they use a proximity fuse to detonate beneath the ship. This detonation vaporizes the water around the torpedo and creates a high-pressure, high-temperature steam bubble, as well as an intense shock wave beneath the keel. When the detonation occurs below the keel, the resulting pressure wave of the explosion lifts the ship, weakening its keel in the process. As the steam bubble collapses, the ship is sucked down by negative pressure and appears to momentarily sag in the middle. When the steam bubble finally reaches the surface, it explodes through the hull of the ship as the change in pressure creates another more powerful shock wave. This combined effect often breaks smaller targets in half and can severely disable larger vessels.
Yeah, it's interesting. In summary, Main design loadings for hull structures are vertical bending moment, horizontal and torsional moment, shear force as hull gutter loadings. As impact loading, bar flare, impact, bottom framing, collision, grounding, explosion, and so on. And as cargo loadings, various kinds of cargoes such as LNG, LPG, liquid hydrogen, liquid carbon dioxide, ammonia, etc. These photos show the liquid hydrogen carrier and ammonia carrier, which have been recently developed. Thank you for your attention. I hope this presentation could have help you understand hull strengths and basic concept. Thank you.
Very much, Professor Bach. Student, do you have any question to Professor Bach? You can say by speech or you can type in chatting window. Said to be none. No, then we can close the invited speech today. Thank you very much, Professor
Thank
Bach.
you.
Right, then we can close our session today. And see you on Thursday at the classroom. Right, bye now.